welcome to this problem walkthrough. In this session, we'll tackle a coding challenge from LeetCode, problem number 1260, titled Shift 2D Grid. Together, we'll explore the problem statement, review different approaches, and analyze their complexities. Let's dive in and get started. In this problem, you are given a 2D grid of integers with dimensions mxn and an integer k. Your task is to shift the grid k times according to a specific rule. In each shift operation, the last element in the grid moves to the front, and all other elements shift one position to the right. After performing k shifts, you need to return the resulting grid as a 2D list of integers. The input consists of the 2D grid, where each row is a list of integers, and the integer k representing the number of shifts. The output should be the updated grid after applying all the shifts. Let's look at an example to clarify. Here, the grid is a 3x3 matrix containing the numbers from 1 to 9, and k is equal to 1. The grid starts out like this: row 1 contains 1, 2, 3, row 2 contains 4, 5, 6, and row 3 contains 7, 8, 9. The task is to shift the grid one time, so the last element, 9, will move to the front, and all other elements will shift one position to the right. After performing one shift operation, the last element, 9, moves to the front of the grid. All the other elements shift one position to the right. The updated grid is now: row 1 contains 9, 1, 2, row 2 contains 3, 4, 5, and row 3 contains 6, 7, 8. In the second example, the grid is larger, containing 4 rows and 4 columns, and k is equal to 4. The task is to perform 4 shifts on this larger grid. Initially, the 4x4 grid contains the numbers arranged as follows: row 1 contains 3, 8, 1, 9, row 2 contains 19, 7, 2, 5, row 3 contains 4, 6, 11, 10, and row 4 contains 12, 0, 21, 13. After 4 shifts, the rows are rotated to create the updated grid. The new arrangement is: row 1 contains 12, 0, 21, 13, row 2 contains 3, 8, 1, 9, row 3 contains 19, 7, 2, 5, and row 4 contains 4, 6, 11, 10. In the third example, the grid is once again a 3x3 matrix containing the numbers from 1 to 9, but this time k is equal to 9. Notice that the total number of elements in the grid is also 9. This means that every element will return to its original position after 9 shifts. As a result, the grid remains unchanged, and the output is the same as the input. Row 1 contains 1, 2, 3, row 2 contains 4, 5, 6, and row 3 contains 7, 8, 9. Now let's consider some edge cases. First, if k is 0, no shifts are performed, and the grid remains unchanged. Second, if k is a multiple of the total number of elements in the grid will also remain unchanged, as every element will return to its original position. Third, for small grid sizes, such as a 1x1 grid, the grid will always remain the same regardless of the value of k. Lastly, the grid may contain negative or large values within the range of -1000 to 1000, and the algorithm must handle these values correctly without any issues. To tackle the problem of shifting a 2D grid, one straightforward method is the brute force approach, where we simulate each shift step by step. The idea is simple: every shift involves taking the last element of the grid, moving it to the front, and shifting all other elements to the right by one position. To implement this, we first flatten the grid into a 1D list, which allows us to manipulate the elements more easily. Then, for each of the k shifts required, we remove the last element in the list and insert it at the beginning. Once all k shifts are completed, we reshape the modified 1D list back into the original grid dimensions. While this approach is easy to understand and implement, it has a major drawback. The time complexity is k*m*n, as we need to process every element during each of the k shifts. This makes the approach inefficient for large grids or when the number of shifts is substantial. Additionally, the method requires m*n space for the flattened list, which may not be ideal for memory-constrained applications. Overall, while simple, this brute force method is not scalable due to the redundant work involved in simulating each shift individually. A more efficient solution revolves around leveraging modular arithmetic to directly compute the final positions of elements after k shifts, without simulating each step. The key insight here is that shifting k times in a grid of size m by n is equivalent to rotating the grid k modulo m*n times. By flattening the grid into a 1D list, the problem becomes simpler, it's just a matter of rotating the list. The new position of each element can be calculated using modular arithmetic, avoiding unnecessary intermediate steps. To implement this, we first flatten the 2D grid into a 1D list. Then, we compute k modulo m*n to determine the effective number of shifts. Using this value, we slice the list at the rotation point. The last k elements are moved to the front, while the rest follow. Finally, we reshape the modified 1D list back into the original grid dimensions. This approach is not only more efficient but also avoids redundant operations, making it well suited for larger grids and values of k. When analyzing the complexity of this optimized approach, the time complexity is O(m*n), as we process every element once during the flattening and reshaping steps. The space complexity is also O(m*n), which is needed to store the flattened 1D list. Compared to the brute force method, this approach is significantly more efficient, particularly for large inputs. However, the trade-off lies in the need for a solid understanding of modular arithmetic and index mapping, which might feel less intuitive for some users. An alternative worth mentioning is the in-place rotation method, where we attempt to perform all shifts directly within the grid itself, avoiding the need for a flattened list. While this can reduce space usage to 1, it introduces significant complexity in handling the index calculations and is prone to errors. The time complexity remains O(m*n), but the added complexity in implementation makes it less practical for this problem. Overall, while space efficiency is improved, the in-place approach is harder to implement accurately. Given the options, the optimized approach with direct index mapping is the preferred strategy for solving this problem. It is efficient because it avoids redundant computations by directly calculating the final positions of elements. The use of modular arithmetic and a flattened 1D representation of the grid provides a clean and simple implementation, making the solution accessible without unnecessary complexity. Furthermore, this method scales well, performing effectively even for large grids and high values of k. The brute force approach, while simple to understand, is too inefficient for practical use in larger scenarios. On the other hand, the in-place alternative, though space-efficient, introduces unnecessary complexity and is prone to errors. By striking the right balance between efficiency, simplicity, and scalability, the optimized approach emerges as the best choice for this problem. To tackle the problem, we need to understand the process of shifting elements in a 2D grid. The task involves taking a grid with m rows and n columns and performing k rightward shifts. A single rightward shift means the last element in the grid moves to the front, and all other elements slide one position to the right. This is repeated k times, and we need to return the final grid configuration. The brute force approach to solve this is straightforward: simulate the shifting process directly. The first step in this approach is to flatten the grid. By converting the 2D grid into a 1D list, we simplify the task of shifting elements. Instead of dealing with rows and columns, we can treat the grid as a single sequence of elements. For a grid with m rows and n columns, this flattened representation will have m*n elements. Flattening makes the subsequent steps more manageable while preserving the order of the elements. Once the grid is flattened, the next step is to simulate the k rightward shifts. For each shift, the last element of the list is removed and inserted at the front. This operation ensures the elements move as required, but it takes n time for each shift, where n is the total number of elements in the grid. Performing this process k times can therefore be costly for large grids or high values of k. After completing the shifts, the final step is to reconstruct the grid. This involves converting the 1D list back into its original 2D form. We divide the flattened list into m rows, each containing n elements, to recreate the grid structure. The result is the shifted grid in its required format, which is then returned as the solution. To optimize this process, we can leverage a key insight about repetition cycles. Specifically, after m*n shifts, the grid returns to its original configuration. This means we can reduce the number of shifts by taking k% m*n. For example, if k is 10 and there are 6 elements in total, performing k% 6 gives us 4, so only 4 shifts are necessary to achieve the same result as 10 shifts. Another important insight involves flattening the grid. By converting the grid into a 1D list, we simplify the indexing process. Instead of working with row-column pairs, we use a single index, which makes shifting operations more intuitive. Finally, reconstructing the grid after the shifts ensures the solution matches the problem's requirements. This involves reshaping the 1D list back into a 2D grid with the correct dimensions. The data structures used in this approach are straightforward but crucial. First, the flattened list is a key component. Flattening the 2D grid into a 1D representation reduces the complexity of the problem, allowing us to handle the elements as a simple sequence. This makes shifting operations much easier to implement. Second, reconstructing the 2D grid from the flattened list ensures the output aligns with the input format specified in the problem. This step is essential because, while the shifting operations are performed on the 1D list, the final result must be presented as a grid with m rows and n columns. Together, these data structures help us manage the problem efficiently and ensure correctness. The key operations in this approach are flattening, shifting, and reconstruction. Flattening involves iterating through all the rows and columns of the grid and appending elements to a 1D list. This operation takes m*n time, where m and n are the grid dimensions. Shifting is the most time-consuming step in the brute force approach. For each shift, removing the last element of the list and reinserting it at the front takes n time, so performing k-shifts results in a total time complexity of k*n. Finally, reconstructing the grid involves iterating through the 1D list and grouping elements into rows to form the 2D grid. This also takes m*n time. Therefore, the overall complexity of the brute force approach is k*m*n. However, an optimized approach avoids redundant shifts by directly computing the new indices for each element based on k%m*n. This reduces the overall complexity to m*n, making it much more efficient for large grids or high values of k. This Python implementation solves LeetCode problem number 1260 Shift 2D grid efficiently. Here's a detailed breakdown of the solution. 1. Input dimensions and total elements. We begin by extracting the dimensions of the given grid, m rows, and n columns. The total number of elements is calculated as m*n. 2. Modulo operation. The k% equals total underscore elements step ensures that we only perform the necessary number of shifts. For example, shifting a grid of size 6 by k equals 7 is equivalent to shifting it by k equals 1, as 7% 6 equals 1. This avoids redundant computations. 3. Flattening the grid. The next step is to convert the 2D grid into a 1D list using list comprehension. We traverse through each row I and column j and append these elements to form a flat list. 4. Shifting the flattened grid. The core logic lies in shifting the 1D list. Using slicing, we extract the last k elements, flat_grid, k, and append them to the start of the list, flat_grid, k, effectively performing the shift. 5. Reconstructing the 2D grid. Finally, we reshape the shifted 1D list back into the 2D grid format. Using another list comprehension, we group every n elements into a row. Each row corresponds to the index range i*n2, i+1*n in the flattened list. 6. Returning the result. The resulting 2D grid is returned as the output. This approach is efficient with a time complexity of m*n for flattening and reconstructing the grid. The space complexity is also m*n due to the additional flattened list. The implementation handles edge cases like k equals 0 or k being larger than the grid size automatically via the modulo operation. Here, we start by importing the necessary packages and defining our solution class along with the shift grid method. The method takes a 2D grid and an integer k as input. We begin by determining the dimensions of the grid, m and n, which represent the number of rows and columns respectively. From these, we calculate the total number of elements in the grid. Next, to optimize the shifting process, we use the modulo operator to reduce k to its effective value, avoiding unnecessary full rotations. To simplify the shifting process, we flatten the 2D grid into a 1D array. We initialize an empty array, flat grid, of size equal to the total number of elements. Then, using nested loops, we iterate through each cell of the grid row by row and populate the flat grid array. After flattening, we prepare to perform the shift operation. We create another array, shifted, to store the result of the shifted values. For each index in FlatGrid, we calculate its new position in the shifted array using modular arithmetic, ensuring that the values are wrapped around correctly when they go beyond the array bounds. Now that we have the shifted 1D array, the final step is to convert it back into a 2D grid format. We start by initializing an empty list of lists called result, which will store the rows of our final grid. Using a loop, we iterate over the number of rows in the grid. For each row, we create a new list to hold the current row's elements. Within this row, we use another loop to add the appropriate values from the shifted array by calculating their original positions in the flattened structure. Once the row is complete, we add it to the result list. After processing all rows, the result list represents the fully shifted 2D grid. Finally, we return this result, completing the implementation of the shift-grid method. To solve the problem, we start with a simple example. The input grid is a 3x3 matrix, and we need to shift all elements by one step. First, we extract the dimensions of the grid. There are 3 rows and 3 columns, giving us a total of 9 elements. Next, we simplify the number of rotations by taking the remainder of k divided by the total number of elements. Since k is 1 and less than 9, it remains unchanged. After this, we flatten the 2D grid into a 1D array to make shifting easier. This gives us a linear representation of the grid as 1, 2, 3, 4, 5, 6, 7, 8, 9. The flattening process allows us to visualize the grid as a single sequence of numbers, which simplifies the shifting operation. Now, we perform the shift by separating the last k elements and placing them at the beginning of the array. Since k is 1, we take the last element, 9, and append it to the start of the array. This results in the shifted array 9, 1, 2, 3, 4, 5, 6, 7, 8. Once the shift is complete, we need to convert the 1D array back into the original 2D structure. Using the grid dimensions, we reshape the array into a 3x3 grid. The final result is 9, 1, 2, 3, 4, 5, 6, 7, 8. This is the output for the given input and demonstrates how the shifting operation works step by step. In this example, we explore a scenario where the number of shifts equals the total number of elements in the grid. The grid is 3 times 3 with 9 elements, and k is also 9. First, we extract the dimensions, 3 rows and 3 columns, giving us a total of 9 elements. Next, we simplify the rotations using the modulo operation. Since k is 9 and the total number of elements is also 9, the result is k equals 0. This means no shifting is required, as a full rotation brings the grid back to its initial state. With k simplified to 0, we can proceed to visualize the grid in its flattened form. The grid is flattened into a 1D array, resulting in 3, 8, 1, 4, 6, 7, 9, 5, 2. Since no shifts are needed, the flattened array remains unchanged, and we skip the shifting process entirely. The next step is to reshape the unchanged 1D array back into its original 3x3 structure. By dividing the array into rows based on the grid dimensions, we obtain the grid 3, 8, 1, 4, 6, 7, 9, 5, 2. This is the same as the input grid, which makes sense because k equals 0 implies no movement. This example highlights how simplifying the rotations can help us quickly determine when no changes are needed. Here, we examine a grid with 2 rows and 2 columns, resulting in a total of 4 elements. The input specifies k as 5, which is greater than the total number of elements. To simplify, we calculate k modulo total underscore elements, which gives k equals 1. This tells us that only one effective shift is needed. Next, we flatten the 2D grid into a 1D array. The grid 1, 2, 3, 4 is represented linearly as 1, 2, 3, 4. By reducing k and flattening the grid, we've prepared for the shifting step. The shifting step begins by separating the last k elements and moving them to the start of the array. Since k equals 1, we take the last element, 4, and place it at the beginning. This gives us the shifted array 4, 1, 2, 3. Finally, we reshape the shifted 1D array back into the original 2x2 grid structure. Dividing the elements into rows, we obtain the result 4, 1, 2, 3. This completes the shifting process for this example, and the final output reflects the grid after one effective shift. To analyze the time complexity of our solution, we start by breaking it down into individual operations. First, calculating the grid dimensions, such as the number of rows m and columns n, is straightforward and takes constant time, or O1, since it's just a matter of accessing the lengths of the input. Next, the modulo operation, where we compute k% equals total underscore elements, also takes O1 time because it's a basic arithmetic operation. Following that, we flatten the 2D grid into a 1D list using a list comprehension. This involves iterating over all m*n elements, which means the operation takes O(m*n) time. After flattening, we perform the shift on the 1D list. The slicing operation involves creating two slices of the array, which together take O(m*n) time, as we combine all elements of the grid in this step. Finally, we rebuild the grid into its original 2D shape using another list comprehension. This operation also requires O(m*n) time because we process all elements to partition them into rows. So, each major step of the algorithm contributes to the overall time complexity. Adding up all these steps, the dominant term in our time complexity is O(m*n), as it outweighs the constant time operations. When we describe the time complexity in terms of the grid size, it simplifies to O total underscore elements, where total underscore elements is equal to m*n. Now, focusing on space complexity, we start with the input grid, which already occupies O(m*n) space. Then, we create a flattened version of the grid, stored in the flat underscore grid variable, which uses an additional O(m*n) space. Similarly, the shifted version of the array, stored in shifted, also requires O(m*n) space. Finally, the result grid, which stores the reconstructed 2D grid, takes up another O(m*n) space. Aside from these, the temporary variables like m, n, and k use constant space, or O1. Therefore, the total space complexity is determined by the additional arrays in the result grid, leading to an overall space complexity of O(m*n). Comparing this optimized solution to a brute force approach offers some valuable insights. In a naive method, we would perform the shift one step at a time directly on the 2D grid. For each of the k shifts, we would need to update all m*n elements, resulting in a time complexity of O(k*m*n). In contrast, our optimized solution avoids this repetitive work by leveraging modular arithmetic and efficiently performing the shift in a single pass, reducing the time complexity to O(m*n). On the space side, the brute force approach could potentially operate in place, achieving O1 additional space. However, the optimized solution favors clarity and simplicity, accepting O(m*n) space for the intermediate arrays. Breaking this down further, we can examine the best, average, and worst cases. If k equals 0, meaning no shift is needed, the algorithm still performs the flattening and rebuilding steps, so the time and space complexities remain O(m*n). For typical k values, the analyzed complexities hold as O(m*n) for both time and space. Even when k is very large, the modulo operation ensures efficient handling, keeping the complexities the same. To further validate our analysis, we can look at the proof of the big O complexities. The flattened grid contains exactly m*n elements, and every operation, whether it's flattening, shifting, or rebuilding, processes these elements linearly. This confirms that the time complexity is O(m*n). On the space side, the storage of intermediate representations, such as the flattened grid, the shifted array, and the result grid, all contribute to the overall space complexity. Since each of these requires O(m*n) space, the total space complexity is also O(m*n). This big O analysis applies consistently across all cases, ensuring that our solution is both time efficient and space efficient for the problem at hand. When solving the Shift 2D grid problem, a few common mistakes often arise. First, simulating all k shifts directly by explicitly performing each rotation may seem intuitive but is highly inefficient. This approach results in a time complexity of O(n*k), which can easily time off for large values of k. Instead, modular arithmetic can simplify the process. By calculating k modulo n, we can reduce unnecessary shifts and achieve an efficient O(n) solution. Another frequent issue is neglecting edge cases for k. For instance, if k is 0 or a multiple of n, the grid remains unchanged. Failing to account for these scenarios can lead to incorrect results or runtime errors. Handling these explicitly by returning the original array ensures correctness. Lastly, incorrect in-place modifications can cause data loss. Overlapping indices during in-place changes can overwrite data that's still needed. Using a temporary array or the reverse technique avoids this issue and allows for accurate transformations. Next, space complexity requirements are another area where errors often occur. Using an additional array for rotation may violate constraints and problems that require extra space. To address this, the reverse technique comes in handy. By reversing the array in specific segments, you can achieve the desired rotation without needing additional memory. Another mistake is off-by-one errors in calculations. Missteps in modular arithmetic, such as forgetting zero-based indexing, can result in incorrect placements during the rotation process. Carefully double-checking these calculations ensures that elements are repositioned accurately and avoids subtle bugs in your solution. Now, let's consider some key interview insights for this problem. Recognizing patterns is crucial. Rotations and shifts often benefit from modular arithmetic to minimize unnecessary computations. It's also important to discuss trade-offs between time and space complexity. For example, you might need to decide between using extra memory for simplicity or optimizing for in-place operations. Additionally, demonstrating your ability to handle edge cases, such as empty arrays, single-element arrays, or very large values of k, highlights your thoroughness. Be ready to discuss alternative approaches as well, such as iterative shifting, temporary arrays, and the reverse technique. Explaining the pros and cons of each approach shows a deeper understanding of problem-solving strategies. Understanding related problems is another way to strengthen your grasp of this topic. For example, LeetCode 189, Rotate Array, involves similar concepts of array rotations with k-shifts. LeetCode 61 extends this idea to linked lists, requiring you to apply rotation logic in a different context. Problems like LeetCode 867, Transpose Matrix, and LeetCode 48, Rotate Image, further challenge you with index transformations and in-place manipulations. When exploring alternative approaches, the reverse technique is particularly noteworthy. By reversing the entire array, then reversing the first k elements and the remaining elements, you can achieve the desired rotation with time and space. However, this approach requires careful attention to indexing, which can be error-prone but is highly efficient in terms of space usage. Finally, let's look at two more alternative approaches. The cyclic replacement method involves iteratively moving elements to their final positions using modular arithmetic. This approach also achieves time complexity and space complexity, but it can be challenging to implement correctly, especially for beginners, as it requires careful handling of cycles. On the other hand, using an extra array provides a straightforward solution. By creating a new array and placing elements directly in their rotated positions, you can simplify the logic. However, this method increases space usage to which might not be acceptable in space-constrained scenarios. Each approach has its trade-offs, so understanding their strengths and limitations is key to adapting to different problem requirements. Great work! In this session, we broke down the problem Shift 2D grid, explored the brute force approach, and discussed key concepts like matrix transformations and modular arithmetic. Mastery of such problems will strengthen your skills in tackling grid-based challenges. Thanks for watching, and don't forget to like, subscribe, and share. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!